Hey everyone, what's up? This is Zachy from Zachy Zone. Today we're going to talk about DPOPS Explained. I wanted to give kind of an explanation, like if someone comes up to me on a convention, says like, what is DPOPS? Or just kind of a brief explanation of it in my own words. So let's get started with this one because it's going to take a little bit of time, but we're obviously going to abbreviate a lot of stuff. So essentially, DPOPS is DPoS, Delegated Proof of Stake, plus Dbft, Delegated Byzantine Fault Tolerance, plus VRF, Verifiable Random Functions, plus a bunch of other stuff, and some modifications to each of those protocols. So before we do that, let's talk about the messaging system real quick. Essentially, it's a server, has a bunch of routes. When messages come in with that route or with that message title, it will find the correct route, do something, send data back or not send data back, depending on what happens. When a browser is talking to a delegate, it's using GET request on the HTTP protocol. When a XCASH core or a delegate is talking to a delegate, it's using a raw kind of my own custom protocol for a TCP socket. I don't think we really need to explain more about that, but just to be real brief, essentially a socket is a pipe between two computers that share data. You can pick TCP or UDP. UDP's like has non-error stuff and is more for multimedia. TCP is more for data, so we're using TCP. From there, that's all you need to send data. The only addition to my custom protocol is I have a termination string because obviously you need to know when a computer's done sending another computer a message. That's all my protocol is because we built this for speed. HTTP protocol is basically a termination string plus a bunch of headers at the top that tell the server how to respond. So my server doesn't rarely recognize any of those from the GET request, but that's basically how all the messaging is working. So now let's talk about the DPoS, Delegated Proof of Stake. And that's basically the voting. So that, like, we have to understand that is basically the voting section, and basically the election section, but it doesn't have anything really to do with the code per se. It's just basically how do we get to the 50 delegates. Obviously, it's included in the code, but you see what I'm saying. It doesn't have anything. It's just a different section. So in Delegated Proof of Stake, you basically can vote for yourself or vote for others. One coin is one vote on this system. And then basically top 50 people that have the most votes are the elected people that will produce blocks. Some systems don't want you to vote and have other people get rewards back. We have built a shared delegate website that will automatically pay back the people who voted for you depending on how much they voted and for each block that they stayed with you. So we kind of made it easy for everybody because that was a complaint I saw in most DPoS systems was either they didn't like it when you voted if you got paid back, or it was hard for the delegate to figure that out. So we just made it automatic. And then the way we're doing the voting, since this is a privacy coin, is we're using reserve proofs from Monero. And essentially that's just, without going into detail on that, it's just basically a mathematical proof that says I have at least X amount of XCASH in my wallet. However, I have modified it for DPOPS to say I have X amount in my wallet. Since in version 1 you can only vote the full balance from one wallet, so I did a little modification on that. So that's basically DPOS. The only caveat on my system that we built is essentially that you have to be online, because I've seen some that were like you can be offline and still produce a block or something like that. So we decided that it'd be best if we did an online check as well. So it sorts you by online first, then it sorts you by how many coins you have voted towards you, and then if worst case there's a tie, which probably won't happen, but there is, it does an alphabetical sort on your public address. So then I guess we should talk about the VRFs. That's probably the easiest one to tackle next. So essentially in most DPOS systems, it's basically a turn-based system. I think that's how all of them were when I researched it. So that just, or round robin, whichever one you're more familiar with. Some of us sports guys know the round robin one. But basically it's, you have 50 people, and what it would do is just say, 1 gets the block, 2 gets the block. It would go all the way to 50, then it would come back. 1 gets the block, 2 gets the block. So I didn't like that for a few reasons. Number 1, it's not fun. Number 2, it's not secure, because if each delegate's going to get the block at a certain time, you could just DDoS one delegate. I'm sure there's probably backup things, but still. And it's not really, I don't know, it kind of seems mechanical and not fun, right? At least in mining it's fun because you don't know, you can go an hour without finding a block and stuff like that. So essentially we changed it. You can't obviously use a random number generator or even a secure random number generator because everybody's going to generate a random number, right? So we just basically use it off of the verifiable random functions. There's a lengthy process we do that with, but just to know that verifiable random functions are basically, it's verifiable that the random number you generated was random based on the input you fed it. So it basically will prove that you've correctly produced the random number. That's essentially what's going on there. So all this data is stored, all the VRF data is stored on a decentralized database, including the entire block itself. So we actually have 2 copies of the whole blocks and transactions, which is kind of cool. We'll explain that in a minute. But all of that's stored, and you can look it up on the website, the Delegate's website for each block, and you can, if you want, compute all the results. But that would take a long time to do by hand, but it's all written down in tables and stuff for you, so that it is verifiable. Because obviously, if it's just verifiable between the 50, then that wouldn't be a good thing. So yeah, it's all stored, it's all verifiable. I didn't see any other coin doing that, so I thought that'd be a cool thing to do. Keeps with the transparent theme and all that. So then let's go over the I guess let's go over the database. So the database, decentralized database, is exactly what it is. It's a database shared among the 50. And what that's doing is what's stored in that. It's basically all the data to prove that a round went correctly. That's the best explanation to say it. And then it's also the entire block and all the transactions. At the same time, we keep our normal chain that has the entire block and all its transactions, but we have a different, I wouldn't call it a different chain, that's probably not the right word, but it's a different blockchain, essentially that's non-needed for the regular people. Obviously, because it grows at about 9, if we do 50 delegates, it grows at 9 gigabytes a year. Obviously, we don't want the blockchain growing at 9 gigabytes a year. That's going to be crazy for people to download, for exchanges to download, for all of that. So it's more as if you're a delegate, you're kind of agreeing you're going to download that data and store that data. And then the regular people don't need to store that because it would make it's kind of stupid, right? The other thing is, what do we store in there to relate it to the other one? We'll talk about that in a minute. But what we store in there is a hash of the entire thing. That's the entire block plus a VRF. That's stored in a decentralized database. We take a hash of that. We store the hash inside of the block. That's on the XCASH core. That way, you're able to link them together. We'll explain. It's also for security purposes. What that does is it adds 128 megabytes a year to this chain. So it's only 128 megabytes, not that big of a deal. It's adding 9 gigabytes on here. Because at first we thought we could just store everything in here. Then we quickly realized, well, if we want to make it transparent and keep it all provable and stuff, it's going to be 9 gigs a year. That's impossible. So we'll do a remote kind of thing with a hash. So there's two parts left to this. One is like how a round works, and then one is how we got how did we shift CryptoNote from proof of work to a delegated proof of stake. So let's talk about that one. That one's the most interesting in my opinion, because it was the most like thinking and creativity that had to go into this. Me and Gillum probably had like 15 calls on this. So essentially how this works is what we've decided to do is you take the difficulty, brief thing on that since this is a blockchain topic. Difficulty is basically how much, what it does is it takes a number, and it takes a very large number sometimes. It takes how many hashing powers is on the chain at the time, and it takes into consideration how long you want, how many minutes your coin's supposed to be, essentially, how many minutes you want in between each block, and it'll produce a number that on average will give you that amount of hashing power will take that amount of time to find a result. So obviously the difficulty changes every single block. And that's how proof of work works. You're trying to find a small little nonce, a small little number that will give you the hash of the block. Essentially that's how that works, just to simplify it. So what we've done is we've set the difficulty to 1. We fixed it essentially, static, whatever you want to call it. So it's always 1. So that means that when you submit a block, whatever nonce you pick, it'll always work. It'll never get rejected. Obviously, that becomes a good thing because there is no proof of work in the DPoS. But then the issue becomes anybody could push a block, right? Or you can mine infinite blocks. So essentially what we've done with that is, how do we fix that, is we're using something called an adjacent block theory, which took a while to think of. What this is you take, it's kind of complicated, but essentially when the programs are calculating the 50, they're doing it for the next round, not the current round. They do it at the start of the round, but they're not doing it for that round, they're doing it for the next round. Basically, what it does is it takes, you store the current 50, you store their signatures per se, and you store the next 50 public addresses in the current block. I know it's kind of difficult to understand, but essentially the current 50, you're storing their signatures because they have to sign the block, and you're storing the next 50 people that are supposed to be upcoming, because remember, you've already calculated for the next round. So you're storing their public addresses, and you do that for every block. And then what happens is, when you play two blocks together, back to back, adjacent blocks, since, for an example, I think I learn better with examples, so let's just say this. Block 1, block 2. So block 1 has the current 50 signatures, and it also has the next 50 public addresses. Block 2, same thing. So you get this adjacent block theory because essentially block 1 has the next 50 people, which is round number 2, and then round number 2 has those 50 signatures. So then what you get is, the way to prove a block's legit is, all you gotta do is say, well, if the previous 50 public addresses, if they match the current 50 signatures, and that data is the current block, then that's a match. And obviously if it's not, then it's not. So you don't do it for all 50, right? Because if someone goes offline, then it mess it all up. So that's where we get into Dbft. We'll talk about that in a minute. But essentially it's 67%. It could be 51%. We could change it to wherever we want because it's modified. So I could do 72 or whatever. But it just needs to be over 51. That way it's a majority. So then that's how that works. When I know this took longer than I thought it was going to take, but to explain it. But essentially, so when you get a block in your XCASH core, it's going to have a little hash on it. That hash gets looked up on all the delegates, and it says, hey, like for block 1, is this the correct hash? And then all those delegates will say like, yeah, it's the correct hash, or no, it's not the correct hash. And then essentially that's how it can tell. Okay, if it's 67%, then if it's 67% and it's the signatures match on the adjacent blocks, then it's a correct block. So that's how your blockchain will know. And that's how we stop people from just adding blocks to the chain randomly and all that. So the last thing we're going to talk about is the Dbft part. So the Dbft part is essentially, The best way to explain this is it keeps one chain all the time, or no alt chains. That's essentially what we can say. What it does is it never allows for people to have alternative chains. Or a way it does that is the majority always has to agree on everything in order for something to get done on this system. And if the majority is always agreeing, there is never a second majority, because like if you have 100 people, like you can't, if you have 51 always agreeing on something, then that means 49 will always agree on the other side. So you can't have two majorities. So that's what Dbft is. Basically never alt chaining. The reason to do that, it's to me it's much more secure. And then the other reason to do that is if you mine, once one transaction or one block passes, one block confirmation, the security of that is equal to thousands upon thousands of block confirmations, because you can't, since the majority already agreed we're going this way, you can't ever go another way. Like there's not going to be any chain splits and stuff like that. So there's no reorgs and stuff like that. So that's what Dbft is. And then essentially how we do that in the round is we essentially everybody creates their own VRF keys, temporary keys, public and secret, shares them among everybody. Then everybody creates like a random data, just 100 characters, sends them to everybody. Then we pick, basically using the VRF, we pick one person and we're going to use their keys. And that's basically, that's like the first 3 parts of the round, and all that's doing is basically calculating or seeding the next block producer, which is why we ask for the keys first, because we don't want someone to be able to change their keys or their input based on what they think the output's going to be. And then from there, just basically that person that's elected will create a block. They'll get the base template for the block, and they'll add their public address in there, so it goes to them, the reward. They'll share it with everybody. And then everybody will start working on their own block. They'll start creating all the VRF data that we created in like 1, 2, and 3. They'll add all that in. They'll calculate some other things they need to calculate. And then essentially they will share it with everybody. Oh no, wait, they don't do that. They sign it first. They sign everything off, because you created it, so you're gonna sign it. And then they share all the signatures with everybody, and then they basically check, does everybody have the exact same thing? So we all checked the last time, we just had the base block, and then now this time we're checking, did everybody have the same data for everything, the same calculations, the same signatures? And then if it's 67 or above, we submit it, and then we go to the next round. And then essentially there's there's a backup, so like if the first one doesn't work, we can move to the backup block producer. And then if that doesn't work, we just sit there and wait for the next 5 minutes, and then we continue. It will be 2 different block producers, even though it's the same block. If we have to replay it, I'm using the time to basically change that, plus the beta string, so that will give us a different thing, because obviously if those 2 failed, there was some kind of, they're offline, something happened, so we probably don't want to use them again and again and again. So that's just basically how it works, and then it loops, and then we mine blocks and all that. So that took a little bit longer than I thought in the explanation, but that's basically DPOPS explained. So thank you for watching this video.